Section 1-2 is a review of the stuff we did last year at the beginning of the year. We had done those function stuff, linear functions, degrees, quadratics, polynomials. They touch upon them so quick, and there's even not a ton of examples. So it will be something as we need to. We'll touch upon those particular topics. Good morning. Piecewise functions are something that will come up in this class maybe a little more frequently than we saw in pre-calc. We did do those last year, but that's something we'll talk about in this section. And just some of those rules of transformations that you might have forgotten. So we had reviewed transformations a little bit on the one worksheet, and so hopefully those we're starting to come back to some of those rules. So remember your slope formula. As we go through this, the slope formula will take on slightly different meaning for us as we start to look at the slopes of tangents and how that gives us information about how the graph is moving from left to right. So we have to know that slope formula, that y2 minus y1 over x2 minus x1. This symbol that you see right here, this little triangle, is the Greek letter delta. In calculus, it refers to a change in. So when I see this, I think of the change in y over the change in x. That delta notation is a notation we're going to see when we get to something called a derivative, and it looks very much like what you see here. There's two major types of notations that we'll use. One is the one notation that was kind of more used by Newton, and then there's another mathematician named Leibniz. So he used a slightly different notation. And sometimes one notation is preferred over the other, and so I just wanted you to see that delta notation now refers to how did the y change, how did the x change. So there's your good old slope formula. Some equations that we need about linear equations. I prefer, and I will use many times, the point slope formula will be very helpful to us. As we start to explore tangents and equations of tangents, that's my go-to formula, y minus y1 equals m times x minus x1. So what do we know? Well, for that one, we're given a point, x1, y1, and we're given the slope. And so then we can just plop that into that formula and get the linear equation kind of in one step. So I do tend to use that point slope formula very often if anything needs us to find a linear equation. For graphing purposes, I think the slope-intercept form is probably our most efficient. Some things that could be helpful there is, remember, m is our slope. Our y-intercept is the point 0b. You want to think about that y-intercept as a point. The reason we want to think about that as a point is because so we can think about it as a starting point for our graph. So that's 0b. Standard form is used a little less often as the other two, but some little pieces that might be helpful to you. If you looked at the standard form and you wanted the x-intercept, so I tend to, when I'm doing standard form, I tend to do what I call a 0-0 chart. The x-intercept is always going to be c divided by a. Think about if the y term's gone, how would you solve for x? You would divide off the a and c divided by a. The y-intercept will always end up being c divided by b. And the slope of this line, interestingly enough, is always going to be negative a over b. So just a little pieces and parts, a quick way to find some information for a standard form equation. But that's why the A, B, and C, for them being visible like that. And what's interesting, in true standard form, the A is always positive, and then the A, B, and C have no common factors. So then you get a fraction that is in correct form instantly because you don't have to reduce it, and there's no common factors. Remember that a vertical line, the y, you don't see the y, it's always x equals a number. The horizontal line is always y equals a number. So if we take the standard form equation and put it, if it's a vertical line, you will not see the y. So that's why it's x over c. If it's a horizontal line, you won't see the x, you'll only see the y. That's why it's by equals c. So vertical lines, x equals a number. Horizontal lines, y equals a number. So as far as linear equations go, one other piece I think I should probably remind you. Here the slope is undefined, so you'll get some number over 0. Here the slope is 0. 0 is a legit number, 0 on the top. So for this one you might get 0 over 5. For this one, you might get 5 over 0. So 0 in a denominator is undefined. 0 in a numerator is perfectly fine. It's just a number. It's just 0. So let's look at our first example. Example 1.12 says to consider the line passing through the points 11, -4, and -4, 5. We're going to find the slope. We're going to find the equation of it in point slope form and slope intercept form. Okay. So if we do part A, we're going to use y2 minus y1 over x2 minus x1. It does not matter which point you choose to be your x1, y1, and x2, y2. If the points were somehow lined up from left to right, it is sometimes helpful to go and make your x1, y1 your leftmost point and the other one your rightmost point, but it doesn't matter. Just pick on one, and that's where you want to continue. So if we plug those into our slope formula, it's going to be 5 minus -4, so that's going to be plus 4. And then it's going to be -4 minus 11. So that's 9 over -15. Now, it's most helpful to reduce. So if it is possible to reduce something, I would suggest doing that. So they're both divisible by 3. So divide that and get, and then it's technically, fractions have the negatives in the numerator or out in front. So our slope is -3/5. So the change in y over the change in x, I am changing in the y direction down 3, and for every 5 that I go to the right. Okay, next, let's talk about part B. Find the equation of the linear function in point slope form. Point slope, remember, is y minus y1 equals m times x minus x. So we had to do the slope formula anyway in part 1 in order to put the stuff into the equation. So where the m is sitting, I'm going to put that right there. Where the x1, y1 is sitting, I'm going to use the point that I originally called x1, y1 anyway. Now, here you don't have to choose the 11, -4 point. You could also use the -4, 5 point, and that's fine too. You pick a point. I tend to try to pick points that are positive sometimes, or if there's a 0 in there, I try to pick the nice numbers. So let's plop stuff in. So we get y minus -4 would become plus 4, and then -3/5, and then x minus 11. Now, if they say point slope formula, you're done. I don't need anything else. That's it. If they just say find the equation of the line and don't specify, that's it. You're done. I don't want you to get in the habit of immediately having to put it into slope intercept form. It's not necessary unless they ask you, like in part C. Or if I was asked to graph it. Otherwise, it's just not necessary. Just do your thing. Okay, so if I want to put it in point or slope-intercept form, just do algebra. Distribute. So the second piece will become a positive, and just leave it 33 over 5. Now, if we relate it to fifths, 4 times 5 is 20. So we're going to subtract 20 fifths from both sides. Why not make it fifths right off the bat so you don't have to mess with it later on? And 33 minus 20 is 13, so that's going to be 13. So if they ask me to graph at this point, I could graph it pretty quickly. Let's go ahead and let's see if I can get my graph. So I need 11 to the right. I think this might allow us to fit here. Let's try. So what do we do? What am I going to do? Let's put the points on, and then let's see if our final answer for C matches up. So 11, 4. I'm almost there. I have to go off my chart a little bit. So it's right there. And then negative 4, 5. And then let's connect them. And then let's see if everything matches up. Okay, so 13 fifths. 13 fifths is 2.6. Did I hit about 2.6 on the y-axis? Yeah, so that's good. From a nice point here, this is a nice point, I should be able to count down 3 and over 5 and hit the line. I did. So this point is here. I can do it again. Down 3, over 5. And then finally one more, down 3, over 5. So everything that I did, the original point lines up, the slope lines up, the intercepts line up, so checking your work for a linear equation is pretty easy. Any questions about example 1.12? Okay, let's keep going. Remember your quadratic formula. What is considered a quadratic equation? Well, if we have the form ax squared plus bx plus c. So if we think of quadratics, you want to kind of think of parabolas. You want to think of that U-shaped graph. The solutions of that equation are always going to be able to be found using the quadratic formula, negative b plus or minus the square root of b squared minus 4ac over 2a. The a, the b, and the c are your coefficients up above. If the b squared minus 4ac gives you 0, that means that you only have one solution. And if we were to graph it, so if b squared minus 4ac equals 0, that means we're only going to be touching the x-axis in one spot. If b squared minus 4ac is less than 0, that means that our parabola is either too high or too low, and it will not have a real solution. If our b squared minus 4ac is greater than 0, that means that our parabola is going to hit the x-axis twice. So that b squared minus 4ac, that they call it the discriminant, this portion right there, is probably the most informative as to what your real solutions are to this equation. So if they just say the nature of the solutions, how many solutions are you going to have, you really just can look at the b squared minus 4ac. If they want you to find the solutions, you have to use this formula. And if this is a factorable quantity, like if you can break it apart into two pieces, that's the most efficient way to solve a quadratic. Factor it. If it's not factorable, jump to that formula. Some teachers teach the completion of the square, completing the square. It's a wonderful technique, but it's not very efficient. So if you can break it up, break it up. If you can't, use the quadratic formula. So let's look at some polynomials. One's a quadratic, one is not. Basically, they want to talk about the end behavior. So I do want to talk about that a little bit. It says, for the following functions, describe the behavior of the ends, because it's as x goes to plus or minus infinity. Find the zeros and sketch the graph. Okay, so let's start with part A. Your lead term, you might recall, in this particular one, the degree is 2. The lead term is negative 2x squared. Now, what does that tell us? Well, that tells us that either both ends are pointing upward when a polynomial degree is even, both ends are pointing upward, or both ends are pointing down. By doing nothing else about part A and just looking at that lead term, that highest power, we know that both of our ends should be pointing downward. Okay, so that's what it first tells us. Both of our ends should be pointing downward. So when we do the first step, they asked us to describe the end behavior. So as x goes to positive infinity, the y is going down to negative infinity. As x goes to the left, negative infinity, the y is also going down to negative infinity. That's the only description I need. Using that arrow notation is fine. We will eventually do a limit notation when we get to limits in a further section. Okay. For part 2, the zeros. Find all the zeros of the function. To find the zero of part A, if it is a factorable quantity, my suggestion would be to factor it. Now, if we think about from back in pre-calc and college algebra and algebra, this is factorable if these two the outer two multiply together, and there's some way to sum the factors that you use to multiply to get those two that will add up to the center. Well, in this particular case, the factors of 2 are 2 and 1. They always add up to 3. There's no other choices. So that's not a 3 in the middle. There's no way to factor that. So remember, the two ways you want to solve a quadratic are either to factor it or to use the quadratic formula. That's not a factorable quantity. So we can immediately jump to the quadratic formula to find the zeros. So the zeros are, so now let's look. In this particular one here, our A is negative 2, our B is 4, and our C is negative 1. Now let's plop that into the formula. So it's the opposite of B, plus or minus the square root of B squared, so why not just square it in your head? That's 16. And then do the math. Negative 4 times A times C in your head. You guys are smart enough and quick enough to do that. Negative 4 times A is negative 2 times negative 4, 8. Times C, negative 8. So just put minus A. Over 2A's is negative 4. So we get negative 4 plus or minus the square root of 8 over negative 4. Okay. The square root of 8, is 2 square root of 2. The two negatives can divide out because a negative divided by a negative is a positive, and a plus minus divided by a negative is still a plus minus. So I would probably write that as 4 plus or minus 2 square root of 2 over 4, and then divide it by 2. So you get 2 plus or minus 2 square root of 2 over 2. No, that one would go away. Okay. I divided by 2, so I have to divide everything by 2. So, so this, if we reduce, you can reduce as long as each piece is divisible by the same thing. So I divided that piece by 2, that piece by 2 became a 1, and that piece by 2 became a 2. I just reduced that. Okay. It's in reduced form. Those are the zeros. If I were to ask to graph it, so step 3 is to sketch the graph. So I'm going to do the graph of A right here. I can't graph this unless I know what those are. Okay, so let me tell you. So now is where you would need a calculator. Okay, so 2 plus square root of 2, divide that by 2, and you get 1.7. Now we're just going to go to the nearest tenth. And then 2 minus square root of 2, get that value, and then divide that by 2, you get 0.29 or 0.3. Okay, so what do we know? We know the ends are pointing downward. If I were to graph a quadratic, I might want to know the vertex. So the vertex is negative b over 2a. So negative b over 2a, let's look at our b's and our a's. So that would be negative 4 divided by negative 4, or 1. So if I plug 1 into that, you really just need the zeros and the vertex to graph a parabola even remotely accurately. So if we plug in 1, what do we get? Negative 2 plus 4 minus 1 is also 1. Does that sound legit? 1. So let's graph it. So put on your vertex. I know I have a 0, or I hit the x-axis at 0.3 and 1.7. So 0.3 and 1.7. So we get this. We could also do the y-intercept. That's another good point on any parabola. Sorry, if I plug in 0, for that one I get negative 1. That's a good point. So there's, because we know it's pointing downward because of that lead term. So that is example A. Now, example B, let's explore that one. So for example B, the lead term is x cubed, and when the degree is 3, I know that the right end's pointing up and the left end's pointing down, and there might be some bumps along in there, but I know eventually the right's going up, the left's going down. So let's describe that end behavior. So as x goes to the left, well, I did right first up here. As x goes to the right, positive infinity, the y is doing what? As I go to the right, what's my y doing? It's going up, right, to positive infinity. As my x is going to the left, which is negative infinity, my y is doing what? It's going down to negative infinity. Okay, so that's all I need for the description of the ends. Base that on your lead term. Now let's find the zeros. I'm pretty sure that this one is factorable. And the reason I say that is because I see a 4 on our lowest term and a 3 in the middle. 4 minus 1 is 3, so it's probably going to be factorable. 4, think about the way 4 can be broken. So let's put it in factored form. So if we see where we're really asking ourselves, where is x cubed minus 3x squared minus 4x equal to 0? Now, in order to factor that, always look for a greatest common factor. They all have an x's in them. Let's take and factor out an x, so that we don't have to worry about that common factor. And then you ask yourself, what are the factors of 4? Since this is a quadratic, what are the factors of 4? And is it a possibility that they subtract and give us 3? Yeah, 4 and 1. And so that is a factorable quantity, x minus 4 and x plus 1. And remember, once you have it in fully factored form, and these are each linear factors, we can split them each equal to 0, and they become very simple. So this one gives us a factor of 0. The middle one gives us a factor of positive 4. The last one gives us a factor of negative 1. So that's the main things we need to graph a a cubic. Okay. So let's put what we know so far. And I'll show you some other hints too. Okay. So I know that I hit the x-axis at 0, 4, and -1. I know for sure that the left end's going down and the right end's going up. Do any of my factors repeat themselves? Were there any powers on my factors? No. When they don't repeat themselves, remember that means that it's a slice through, slice through, slice through. So if you look at what I just did, I had to slice through, slice through, slice through. I get a bump here and a bump here. For accuracy's sake, you could plug in -1/2 to find out how high this bump goes. And maybe something in between here. Maybe it's not going to be perfectly accurate, but the middle is usually a good indication of how low or high you go. So you could even plug in +2 to see how low you go. But if they say sketch the graph, just put a bump here and a bump here. If they say to accurately sketch the graph, make sure you find out how high or low those bumps go approximately by plugging something in. There is a way eventually where we will know how, using calculus, to find where the peaks and valleys are precisely. We couldn't do that in a pre-calc class. But in a calculus class, we will be able to locate those high points, low points, those maxes and mins. So there is example 114. Does anybody have any questions there? Does that remind you how to graph some parabola or polynomial stuff? Okay. Let's look at example 115. For example 115, it says, a company is interested in predicting the amount of revenue it will receive depending on the price it charges for a particular item. Using the data from table 1.6, did I even give you table 1.6? Wait a second. I mean, it's in your book, but I don't know if I've, wait, I'll find it. There's 110. Oh, there's 1.6. Okay, I'm going to write down the table from 1.6. Using the table, which I'll give you in a minute, the company arrives at the following quadratic function to model the revenue. So they have taken this table, which I'll put over here. And they have modeled the parabola closest to this table's information. Okay, and they got this equation right here for the revenue for this particular company. Okay, and that particular item. Now, let's look at what the P stands for. The P stands for the price of the item. And what you want, the company wants us to do is they want us to predict or use this equation to maximize their revenue. Okay, so now we got the equation, we got the table. Let's go on to question A. Question A says to us to predict the revenue if the company sells the item at a price of $5 and the price of $17. All they want us to do is plug in $5 and plug in $17. And they've given us that lovely equation, negative 1.04 p squared plus 26p. So they just want you to do that for both 5 and 17. Okay, so they just want us to plug those in to predict what we might be making for those particular items. Okay, so let's look at the first one. If we plug in 5, we get we get $104,000. $104,000. if we sell that item for $17, we get $141,400. Now you might ask yourself, 17 is more than double. It's over 3 times the 5. Why didn't we make more than 3 times the amount? Well, think about supply and demand. That's why our parabola is going to have a peak, and then it's going to come back down. If you start charging too much money, then the demand for your product will go down because people are going to be like, I'm not paying that amount for that product. And so that's why the 5 and the 17, they seem like they would, be slightly, different amounts than that, but they're not that far apart. Okay. Now, B says to find the zeros of the function, interpret the meaning of the zeros. Okay. So we've got this equation, and they ask us to find the zeros. So it is a factorable equation. Let me show you. Where that equals 0, if both pieces have a common factor or a common variable, remove it. So I can remove a p. And then as soon as it's factorable as far as it can go, we can split it up. And then we can just solve each one. If we did, I'm sorry, I made an algebraic error there. If we put this equal to 0, we would have to subtract 26, so that would be a negative 26. And then if we divide by 1.04, let me tell you what we get. We get 25. Okay, so what does that mean? Well, if you think about, this is how much money would I make if that's what I charge? Well, if the price is $0, I'm going to make $0. So my height is 0 there. So that makes perfect sense. Let's talk about the $25. What that means is if I jack the price up to $25, I'm going to sell none of them. Nobody's going to buy them. My revenue is going to be nothing.
Are you breaking even?
Well, if it said profit, if that was a profit equation, we'd be breaking even. We'd have no profit. But if revenue means how much money you're going to be making off of that item, I think, I'm not a business major, but I think that's what my interpretation of is, what money would you be making? And we would not be making any money from that sales.
The way I'd seen it would be the fact that it's a parabola, so you're going to have to go into the negatives, meaning it would cost more to actually make it than it would be to sell it at that price.
Yeah, so this, if you think about, if my price is nothing, I'm making nothing. If the price is 25, nobody's going to buy it because it's too high. So as we go on the parabola, because that's going to be an upside down parabola, as we come here, we're rising the price, but people are still willing to buy it. Here's the best price to make the most money. And then as we're coming back down, it's getting too high, so less and less people are buying it, until nobody buys it. So I think that's the interpretation you want. Okay, and then let's look at part C. Sketch the graph. Okay, so again, for a parabola, we know the lead term is negative and it's a squared, so it's going to be an upside down parabola. I'm going to count by 5s. I think that will be most effective. When I go to graph a parabola, I think I might have to go by 10s. So anyway, if I go to graph this parabola, you definitely want the vertex. We need to know where it goes. We know the zeros are 0 and 25. So we'll count by 5s this way too. 5, 10, 15, 20, 25. Let's look at our vertex. Our vertex has to be halfway in between there. So our vertex has to be at 12.5 something, okay? If you plug in 12.5, because of the symmetry of a parabola, it's always symmetric to the vertex. So what's halfway between 0 and 25? 12.5. If you plug 12.5 into the equation, you get 162,500. So let's count by, I need to go up 16 to do that. Let's count by 20,000s. So like 20,000, 40, 60, 80, 100,000, 120, 140, 160. So there's 160. So we'll just be a little bit above that. So at 12.5 here, so 5, 10, 12.5, we're going to be up at 160. Or a little above that, 162. And then we know it's a parabola coming down. Sorry, that's an ugly parabola. Okay. So then it says, use the graph to determine the value of P that maximizes the revenue. An upside down parabola, by graphing it somewhat accurately and finding the vertex anyway. So this is C. The vertex gives us the answer to a maximum or a minimum of a parabola. If our parabola is upside down, the maximum occurs at the vertex. If our parabola is right side up, a minimum occurs at the vertex. They says use the graph to determine the value of P that maximizes the revenue. So the price that I want to sell it at is $12.50. And what is the maximum revenue? Well, the revenue at that we determined already was $162,500. Okay, so that means, you know, if you were a person interpreting this information for the owners of this company, you would say, based on our data, you know, you should be selling this for $12.50. You'll make the most money. Okay. So that's example 115. So now let's do example 116, and then we'll stop for today. So we've seen linear equations, we've seen some quadratics, we've seen some polynomials. So those are things we've seen in the past. Now let's talk about our beautiful and lovely rational functions. So rational functions, fractional functions that have a polynomial in the numerator and in the denominator, have some problems with them, remember? So the first thing we have to remember is about the domain. So we have to concern ourselves, where does 5x plus 2 equal 0? That's going to tell us the points that we cannot include in the domain. That will be the only points. And if that factor is not also in the numerator, then that will be a vertical asymptote. So if we go ahead and solve that, we know that there is a vertical asymptote at x equals negative 2/5. Okay. Let's think about some other things from back in the wonderful world of pre-calculus. If the power on top matches the power on the bottom, we also know that this one has a horizontal asymptote at y equals 3/5. So it's just those coefficients when the top and bottom match. So that means the left and right ends are heading toward 3/5. The middle pieces are heading toward the vertical asymptote. So we really have a lot of things that we know right now. Okay, so let's put on our x and y axis. And let's go ahead and graph it. So what do we know? Well, there's a vertical asymptote at negative 2/5. So just put your little, not quite halfway through, negative, like about here. Not quite at negative 1/2, but 0.4, negative 0.4. And then there is a horizontal asymptote at 3/5, so put that on there. 3/5 is 0.6, so it's a little bit higher. Sorry, that's so yucky. And then we really just have to know where our swoops are. Do we have a swoop here, here, or is it here and here? Where are our swoops? All you got to do is plug in two things. Let's plug in something over here. Plug in something that's nice. Let's plug in 1. And then let's plug in something over here. Let's plug in -1. If you plug in 1, you get 3 minus 1, or 2. 5 plus 2 is 7. So that means it's a positive thing. If I plug in 1, I'm at 2 sevenths. Did I get that right? Let's see. If I plug in 1, I get 2 over 7. Yeah. And so 2 sevenths, I'm thinking this piece is down here. Because 2 sevenths is below that 3/5. And then -1, I get negative, I'm sorry, what do I get? I get, yeah, negative 4 over -3, and which is 4/5. So that would be above that line. So I'm thinking that piece is right here. And then just take a minute, and I would put it into Desmos to just make sure that your pieces are where you think they are. But as far as the range goes, I'm going to hit any value except the horizontal asymptote of 3/5. So let's write the domain and range, and then we're done. So the domain goes from -infinity until it hits -2/5, the vertical asymptote, and then it keeps going. And the range does the same thing except for a horizontal asymptote. So it goes from -infinity up to 3/5, and then it jumps across that, and then it keeps going. So there's the domain and range. And for certain times, we are going to keep practicing graphing those things. For now, just make sure to think about those rules for vertical and horizontal asymptotes. Okay, so we're going to stop here. We will continue these notes tomorrow. We have still a few more examples to go for this section. Okay, so there you go.